the Dolph-Tschebyscheff excitation for arrays is based on the idea of the Chebyshev polynomials. And I'll tell you in a second what the Chebyshev polynomials actually are, but they have some interesting properties that come from the way that they're constructed. First of all, it starts from the idea that cosine of n times, let's say x, whatever value, always has magnitude less than or equal to 1. Second thing, that expression cosine of nx can also be expressed as a polynomial in cosine of x. So in our book, those are written as t sub n of, we would write cosine x like that as the argument, where t sub n is the nth Chebyshev polynomial Now, putting the argument cosine x into this polynomial means that you end up with something that has some coefficients on powers of cosine of x. And so on. But what if we put a different variable in there? Let's name it z. So because of point number 1, for the region where the magnitude of z is less than or equal to 1, and this is for real z, so that's plus or z between plus and minus 1. Then point 1 still stands, because this Chebyshev polynomial, if you put in something that could represent a cosine, and that would be any number between plus 1 and minus 1, then that polynomial's value is also magnitude less than or equal to 1. In addition, all the zeros are within minus 1 and 1. In fact, I'm going to name that point 4. Point 5, outside that region, minus 1 less than or equal to z less than or equal to 1, the Chebyshev polynomial monotonically increases or decreases. Now, I originally wrote this as the polynomial as a function of cosine of x. And then I said that we're going to replace cosine x with z. Why didn't I just put in x here? The zeros would move around because of the way that cosine moves x around. And also, x wouldn't be fitting within the range -1 and 1 the way that cosine does. So it's better to represent, it's better to replace the cosine by a new variable rather than try to have it operate on x. So that's the reason that we're using Chebyshev polynomials. They have all of their zeros between -1 and +1. Outside of that region, they monotonically increase or decrease. Oh, and the most important thing of all maxima and minima are within that region -1 to 1. And have magnitude plus or -1 respectively. So we have a polynomial, all of whose maxima and minima are the same height, and then within a particular region, and then after that it blows up or it blows down. I'm going to show you a plot of what they look like too. Here's a plot of the first 1, 2, 3, 4 Chebyshev polynomials within the region from -1 to 1. Outside of that region, on the right-hand side, on the positive half of the x-axis here, all of those different polynomials of different orders just continue increasing monotonically. On the left-hand side, 2 of them increase monotonically and 2 of them decrease monotonically. Since we're talking about arrays, we mostly care about the array factor's magnitude. So we don't really care whether it goes up or down. And then the way that we implement a Chebyshev polynomial as an array factor is we choose the size of the window to be slightly bigger than -1 to 1. So within that region, we have our Chebyshev polynomial doing its thing. I'm going to pick this one. And then outside of there, we let it increase beyond that a little bit. We choose our window to be big enough that it is the right height. And the way that we do that is by writing our Chebyshev polynomial as a function of cosine theta divided by some value z0, where z0 is the value over here where the Chebyshev polynomial evaluated at that value is equal to whatever side lobe level ratio we want, called the voltage ratio. So basically, we're going to scale that window and normalize it so that the relative height of these local maxima and minima, which turn out to be the side lobes, is 1 over R0, where R0 is our specified value. And we do that by finding the place where this known polynomial equals the value that we want, since we know that its value within this region is always, its max and minimum values are always plus and minus 1. That's a little bit convoluted, but I wanted to show you what these polynomials look like. I wish I had a picture where they actually zoom out a little bit more, but there is a picture like that in your textbook in figure 6.21. You can see that. So having chosen the right window size, it's pretty easy to then figure out what the weights need to be.